Welcome, my friends. Suppose a car is purchased for $10,000 and the value decreases by 15% each year. After how many years will the car be worth less than $6,000? Write the smallest possible whole number answer. Let's let V of t represent the value of the car after t years. V of t is equal to 10,000 times 0.85 to the tth power. Why 0.85? Well, if the car is decreasing in value 15% per year, that means the new price must be 85% of the price from the previous year, which is 15% less than 100%. The 10,000 is, of course, just the original value of the car, which must be multiplied by 0.85 t times to find the value of the car after some specified period of time. We are asked for when the value of the car will be less than $6,000, so that is a value for V of t. Let's set this equal to $6,000 and see what we get. We have 6,000 is equal to 10,000 times 0.85 to the tth power. Let's divide both sides by 10,000. We are left with 0.6 is equal to 0.85 to the tth power. Now, you might remember that the way that we solve for an exponent is to take the log of both sides. Let's use the natural log. We have the natural log of 0.6 is equal to the natural log of 0.85 to the tth power. One of the properties of logs is that if the argument of a log is raised to a power, that power can be brought out front. So we have the natural log of 0.6 is equal to t times the natural log of 0.85. Dividing both sides by the natural log of 0.85, we have t is equal to the natural log of 0.6 divided by the natural log of 0.85. Let's grab a calculator. We have the natural log of 0.6 divided by the natural log of 0.85, which is equal to approximately 3.14. Recall we were asked to report the smallest whole number answer. Well, we can't round this down to 3 because that would be before we hit $6,000. Remember, the car is decreasing in value, and it doesn't reach $6,000 until 3.14 years. So that means at 3 years, it will be worth a little bit more than $6,000. So that means we need to go to the next year, which is year 4. The value of the car will be less than $6,000 after 4 years. Let's try this one. The mass of a radioactive substance follows a continuous exponential decay model and decays at a rate of 9% per day. A sample of this substance was taken 2 days ago, and the mass is 3 kilograms today. Find the initial mass of the sample rounded to 2 decimal places. Now, be careful here. The problem says that the mass follows a continuous exponential decay model. When you see continuous, you should think E. We talked about continuous compounding in another video and used the formula A is equal to P times E to the RT power. We can use the same formula here, except A is equal to the amount of mass remaining in the substance after the specified period of time, P is the principal or original amount, R is the rate of growth, and T is the time, which in this case is in days. We have A is equal to the 3 kilogram mass that the substance has today, P is the initial mass of the substance from 2 days ago, which is unknown. That's what we're trying to find. R is the rate of growth, but be careful here as the mass is actually not growing, it's decaying. So we have a negative growth rate. R is equal to negative 0.09, which represents our 9% decay. T is the time, which in this case is 2 days. Plugging everything into the formula, we have 3 is equal to P times E to the negative 0.09 times 2 power. Dividing both sides by e to the negative 0.09 times 2 power, we have p is equal to 3 over e to the negative 0.18 power, as negative 0.09 times 2 is equal to negative 0.18. Typing this into the calculator, we have 3 divided by e to the negative 0.18 power, which is equal to approximately 3.59. The initial mass of this substance must have been 3.59 kilograms. Let's try one final problem. The number of bacteria in a certain population increases according to a continuous exponential growth model at 3.4% per hour. how many hours does it take for the number of bacteria to double? We will still be using the same formula. A is equal to P times E to the RT power. But in this case, things are a little different, as we are not given the initial amount of bacteria or the amount of bacteria at the end of the period. Here's what we do know. A is the final amount of bacteria, which we don't know. P is the initial amount of bacteria, which we also don't know. R is the growth rate, which is 0.034. T is what we are asked to solve for, the time it takes for the bacteria to double. So how are we supposed to do this? We have 3 unknowns. Well, you may have recognized that there is one piece of information we haven't used yet, and that is that we are interested in how long it takes for the bacteria to double. That means that A, the amount at the end of the period, must be double P, the initial amount. So you can literally throw in any 2 numbers such that A is twice as big as P, and the problem will work. Let's let A equal 2 and P equal 1, the simplest case where the bacteria doubles from 1 to 2. Now we can build our formula. We have 2 is equal to 1 times e to the 0.034 times t power. The 1 doesn't change anything, so we can get rid of that. The way to get a variable out of the exponent is to take the log of both sides. In this case, the natural log will be the most beneficial, since we have an equation involving e. We have the natural log of 2 is equal to the natural log of e to the 0.034 times t power. One of the properties of logs is that if we take the log of something raised to a power, we can pull that power out front. So we have the natural log of 2 is equal to 0.034t natural log of e. But the natural log of e is just equal to 1, so that part disappears. Now we can divide both sides by 0.034. We have t is equal to the natural log of 2 divided by 0.034. Plugging this into our calculator, we have the natural log of 2 divided by 0.034, which is equal to about 20.39 rounded to 2 decimal places. It will take about 20.39 hours for the amount of bacteria to double. Alright my friends, that wraps up our video covering word problems related to exponential growth or decay.